Welcome to the Andreas Orthey podcast series on robotics. My guest in this episode is Wolfgang Hönig. Wolfgang is a professor at TU Berlin, where he heads the Intelligent Multi-Robot Coordination Lab. In this episode, we will talk about how to coordinate the motion of multiple robots and what the physical effects are on each other, why Wolfgang switched from working at NVIDIA to do academic research, and how he feels about military applications. I'm grateful that he was able to join me. Please welcome Wolfgang Hönig. Welcome, Wolfgang. So you run actually a drone lab here at the TU Berlin. Could you maybe talk a little bit about your long-term goals with this drone lab and what is the purpose of your research?
Sure. Thanks for having me, Andreas. So my research focuses multi-robot systems, and that's a research group. And we often validate on drones, as you said. And we are in particular interested in bringing drones to the real world eventually. So, for example, for applications such as search and rescue, where a swarm of drones could come in and find maybe victims very quickly.
And so how did it actually happen that you stumbled upon robotics as a career? So what actually made you go into robotics and choose this field as your field of research?
Many small steps, but already when I was a teenager, I started working in embedded systems and worked on controls for heat pumps doing the hardware and the software. And I also specialized in computer engineering later during my studies of computer science. And eventually that led to robotics because I find it a very interesting area where you can do hands-on things and software at the same time.
And can we go a little bit more back in your life? So where have you actually been born and how was life growing up for you?
So I was born in Dresden in Germany and pretty much in the suburbs. So it used to be just a small village. And I went basically to school there in Dresden and also to the university in Dresden.
Cool. And so what would you say were like the first point of contact with, I don't know, information technology or robotics? So was there maybe a point in time where you maybe got your first computer and you did a little bit of programming? Can you maybe remember that?
Oh, not the exact specifics, but my parents did have an MS-DOS computer, so that was probably the first time for me. I also had to type in the commands. And maybe as many computer scientists did, I started for a while with just game development. Work and learned basically programming in that context. And shortly afterwards, I basically switched to embedded systems and microcontrollers.
Yes, it's so common to start actually with game development. So can you actually remember what kind of games you were programming like in the beginning?
It was less programming, but more design. And I looked at like traditional car racing.
Okay, so your first game was like a car racing simulation or something?
But let's say the first attempt, I didn't really progress to make a full, complete game.
And then when you were in school, what were like your, I don't know, favorite subjects there? Was it like something like math and physics or?
So I went to a magnet school in Dresden, which was specializing in the sciences and math. So we were basically forced to take a lot of math and also encouraged to participate in competitions. And I did the combination of math and physics. And then in the high school area, we also had classes related to computer science.
And there you already knew that you wanted to go into this area, or was it still that you're a little bit undecided and you decided later on?
Well, like everyone, I was very undecided for a pretty long time, and I just attended the regular university open days where you could learn more about different subjects. And I considered computer science, electrical engineering, or physics as my areas.
And what did you choose in the end?
I did study computer science, and I'm fairly happy with the choice. I sometimes feel there should be a more rigorous math education in computer science. But otherwise, I really enjoyed the combination of theory and also really hands-on practical things that allow you to make something that can change the world.
Yeah. Computer science is obviously pretty big. And then at some point, you must have decided that, well, here's robotics. Maybe this is like a very nice field to get into, to do research in. So how did this actually happen that you actually choose robotics at some point?
Right. So in the school I went to, the Technical University of Dresden, at that time when I studied, did not actually offer robotics. Since I wasn't a professor. So what I specialized in was embedded systems in terms of coursework, which was very closely related and I enjoyed very much. And at the same time, I started a student assistantship in the high performance computing group, where we looked at supercomputers and hardware accelerators for supercomputers. And I found that robotics is quite interestingly somewhat in the middle, right? Because you don't want these like super low-end embedded systems. You really need something more high-end. But at the same time, you can also not put it in a big like warehouse with cooling.
Yeah, that's true. And so what did you actually work on in your master thesis when you finished your university degree?
So I actually did my master thesis with a company, NVIDIA, and I worked on profiling of GPUs, in particular of what is running CUDA. And I developed binary code patches that could tell CUDA programmer, how to improve their CUDA kernels.
Yeah, and it's very interesting because you joined actually NVIDIA after your university, right? And that was at a time when NVIDIA was not really super big, right? So they were already like a good company in computer science, information technology, but they were not as big as they are today. So I guess that must have been still a very exciting time to have been there, right?
Absolutely. And I'm sure even being now there is very exciting.
So what did you actually work on during your time at NVIDIA?
Oh, I had this one-in-a-lifetime chance to take my master thesis and integrate it into a real product. And so basically the code I was working on was integrated in that software tool that's known as NVIDIA Insight, which is part of the profiling tools at NVIDIA. And yeah, I basically took the prototype, integrated it, and then worked on maintaining it for various different GPU architectures.
Nice. And how was actually the company culture at NVIDIA in 2012? I think you went there in 2012, right?
Yes, exactly. Right after I finished my diploma. Yeah, very interesting, very geeky people, very smart people. And I thought the culture was very enjoyable. I learned a lot and I had a great time.
In which city were you actually?
So I started during my master's as an internship in Austin, Texas, and spent the time there, which was also where the primary group was. And then I worked for roughly 2 years in Aachen in Germany.
Oh, so it was in Germany. Nice. So I didn't know that they actually had an office in Germany. Nice.
Yes, so it's an office that they got from a former GPU company called ELSA, which is a bot.
Are there actually maybe like some big lessons which you learned while being at NVIDIA, which have maybe like influenced you still up to this day?
I think quite many. Like a lot of my technical skills I picked up at NVIDIA. I had great mentors who really taught me what it means to write good code, what it means to do code reviews, how to do project management, how to debug systems that are extremely complex, where you may not be able to like simulate everything. And I think I took these lessons then later also for my PhD, for example.
And so what kind of programming language were you actually using at NVIDIA?
So most of the code I was working on was in C++.
Mhm.
And then we also did this binary code patching, which means you had to generate and change basically GPU assembly code.
Mhm. Are you using some coding environments? So what is your favorite one?
I tend to switch every couple of years,
Mhm.
but back then I worked a lot in Sublime Text with almost no extensions.
Mhm.
And these days I'm frequently using Visual Studio Code
Mhm.
with some extensions. But I
Mhm.
do like to look at code more plainly.
Mhm. And so today, NVIDIA is, I think, right now the largest company in the world. Do you think that back in your days, there was already like some kind of evidence or so where you think, okay, this already showed me that they were like going to this direction of becoming this big as they are today?
I think more the opposite. Like NVIDIA has seen in its history a lot, or maybe not a lot, but several cases where they were very close to bankruptcy.
Mhm.
So I was also surprised, like maybe many other people, that it is
Mhm.
now the highest valued company.
Mhm. So how long were you actually in NVIDIA? I think 2 years or something?
Yeah, roughly 2 years.
And then at some point you decided you want to move on, you want to do more like research. So how did this actually come to happen? Was it your plan like all along? You wanted to always go into research?
So after my master's, I was very confident I would not like to stay in academia because I had enough of it. And that's why I was happy to join industry. But this perspective changed a little bit over time. And there were two important aspects. Like the first one was that the work at NVIDIA became a bit more repetitive. So I had implemented the product, but then there were many new GPU versions and generations coming out, and the maintenance got quite not difficult, but very time consuming to do it. So it got a little bit boring, to be honest. And then also for private reasons, I basically met my wife back in these days, and she was going to grad school in the US. So that was perfect timing.
But wait, you met her in Aachen?
I met her in Aachen, yes.
Okay. But at that time she was already working in the US.
Yeah, she was basically an exchange student who was visiting the university in Aachen.
Ah, nice. And then you both decided you wanted to go back to the US?
Yes, I mean, for her, she was basically already almost involved in a graduate program. There was no question. And then for me, that was the perfect timing to say, okay, now I try that thing.
Yeah.
It's called PhD that I hadn't really considered before.
And so how hard was it actually for you to get into a PhD program?
Very, very difficult.
Okay.
Like I got rejected from most places.
So how many times did you apply? How many?
I applied to 4 schools and got accepted to 1.
Okay. Well, that is not too bad, I would say.
Yes.
So which one were you accepted to?
I went to the University of Southern California, which is a school in Los Angeles.
How far is that apart, roughly?
Between what and what?
Well, between those two schools. So where was your wife again?
My wife also went to that school. So we ended up, luckily, at the very same.
Oh, okay. So you were both now accepted in the PhD program at the same school. Okay.
Exactly.
When did you actually move to the US?
In 2014.
Okay. And it was basically your first time in the US?
So I did that internship in Austin, Texas.
Yeah.
Before. That lasted 1 year in total. And so it was.
So you were already experienced in going to the US?
Yes, but a different coast.
Yeah, sure. And so how was life there when you started?
So at the beginning, stressful because you have to kind of settle in not only a new place, but also that whole PhD program. The way it's set up in the United States is that you take classes again at the beginning, and I hadn't taken classes in several years. So it was quite difficult, I would say, to kind of get used to it.
Mm-hmm.
But then after a while, I enjoyed it a lot. I think Los Angeles has a lot to offer for people to live in.
And so the lab which you joined, so what kind of research was developed there at that time when you joined?
So I joined groups that was working on multi-robot coordination with drones. And so I basically had almost no experience with like what you would call robotics. I had experience with these related areas like computer engineering, embedded systems. And so during that time was also where I learned the basics of robotics, like what is even a controller, because we don't teach that in computer science.
Okay, and did you, so when you applied to all those graduate schools, did you wanted to actually do research on drones, or were you mostly like looking to go into research on robotics? Or so what was more important to you, robotics or drones?
I had zero experience with any robotics, so I was not biased. I really just applied to robotics.
Okay. And then you basically started your PhD on drones?
Exactly.
So what did you actually do in the beginning? So what was your first research question? Maybe first paper even?
Yeah, I actually worked at the beginning on mixed reality for robotics. So how can you integrate physical hardware and virtual hardware in some sort of virtual environment, and how is that useful? First paper was even called Mixed Reality for Robotics that outlined 3 different use cases where mixed reality is beneficial. And it was a great starting point because I had to learn like, also different things like how simulation works and so on.
And how does it actually work, mixed reality with drones or in a drone research lab? So what does it actually really mean?
So you have some drones physically flying, typically in an indoor flight space, and it's being tracked by some external system, but you don't put any obstacles in it. And then maybe in your virtual environment, you can add additional drones and also obstacles that might be interacting with at least how the physical drone should be behaving.
So it was not something where you had like virtual reality glasses on and you were like stepping into the drone world, or?
No, I mean, this technology came slightly later, but there was some follow-up works where people looked at also augmented reality and so on.
And then, so this was basically your first paper or your first research, right? And what was actually your PhD thesis in the end about? Was it like something similar, or did you like switch a little bit in between?
I switched a lot. My thesis at the end did not include all of the papers that I had written. And that's also on purpose. So in the United States, you don't really come in and have a fixed research project. It takes the first few years to study more and to also really define your research. And I ended up mostly working on motion planning for multi-drone teams.
And so why did you pick this topic? Did you think this was like the most important one for drones for the future?
Maybe, I mean, most important is hard to define, but maybe the most basic one. Like I felt that if you can't even figure out how to move the drones, then how would you ever do anything useful? And it turned out that that was a problem, at least at the time, was not really solved at all. And it was also, from a technical point of view, very interesting to look at.
So can you maybe tell me what are the main challenges for doing motion planning for drones?
That are remaining?
Well, or let's start from the very basics. So what is actually the main challenges you have to overcome to actually make drones fly around?
Okay, so the nice thing about drones is that in principle they're very simple. So you could do geometric planning, for example, with splines, and then you can follow the splines and everything works out.
Mm-hmm.
It becomes complicated in two settings. The first setting is that you have very fast flight, because then your motors start saturating, you operate very close to the operational limits, and that can cause instabilities in your controller. And the second setting is where you fly in high density areas. So either drones very close to the ground or multiple drones close to each other, because there's also many things that are not that well modeled. So planning becomes very challenging.
So what is not really well modeled in those
the
settings?
Physics, like even the physics, we don't quite understand well if we fly very close to multiple drones.
Can you give me an example of what we don't understand there?
Sure. So if we fly really on top of each other, two drones, then we know that there's a force created for the lower drone, which makes it really unstable. What we don't really exactly know is how we can predict the magnitude of the direction of the force.
So it's mostly like a chaotic system at the point when two drones are flying above each other. Is that basically how you think about it?
I'm not sure if it's chaotic, but it's at least something where our traditional models simply don't work. There's some like fluid dynamics that can apply here, but it's very, very slow.
So you would say that this is definitely one problem which is not yet solved in drone research. Okay. And are there other physical challenges like that which are still needs to be solved? Or would you say this is like the main one right now?
So if you include hardware, there's, I think, many challenges that kind of come from the physics. One is the energy efficiency, which is very, very poor. Another one is just the noise level. Like if you take even an airplane or also like a multi-rotor for a drone, then that tend to be really, which can be unpleasant.
And so what kind of methods do we actually have to move a drone around? And maybe what is your favorite method to move a drone around?
In terms of motion planning?
Yeah, for example.
I think the easiest is really to plan splines and not just follow the splines. And then how you plan for the splines really depends a little bit on your setting, if it's single robot or multi-robot. And if you have obstacles.
And so what does it actually mean to plan for splines? Does it mean that you first have to figure out what are maybe like some waypoints for the drone and then you interpolate those waypoints? Is that basically what you mean with planning with a spline?
That is one option. There's some other options where you define convex free space areas. You try to solve an optimization problem as the curve stays within these convex free areas.
And would you say that this is basically the best way we could ever hope to plan for robots? Or do you think there are still like some better ways out there which we have not yet discovered, where more research could like uncover something? Or do you think this is really the end game of drone motion planning?
I think it's kind of probably the best in terms of computational efficiency, but it's not the best in terms of solution quality. And so what my group and also the community is moving towards is really planning with the full dynamics, where you can take motor saturations and maybe other kind of learned effects more directly into account. And the main downside of these sort of methods is that they're currently too slow to be run in real time.
So I guess some people would now ask you, well, we now have like ChatGPT, we have big data, we have maybe also like some foundational models. So why can't we just learn to fly and then just have like a controller which has been learned, which can basically do all of that? So do we actually need some kind of motion planning or spline planning, or can't we just like put everything into a big neural network and let it figure out what to do?
Yes, people do, and I think it really depends on the application. Like, for example, you can use reinforcement learning and really find very robust policies that can maybe fly in some cases even better than the traditional methods. And at the same time, you can also use language models to maybe add some semantics to, for example, let's fly to the kitchen and see if I have coffee there, these sort of problems. But they all come with downsides that the traditional methods don't have. So reinforcement learning doesn't provide you with safety or stability guarantees. The language models are still, they're on a higher abstraction level most of the time. And if you would move them to the lower abstraction level, you also lack the guarantees that the traditional methods. So my personal feeling is that there's no one winner here. We are striving for combinations of these methods that just make sense.
Yeah, would you say that motion planning has really this advantage of providing safety guarantees? And do you think there would also be maybe a way to combine both of them so that we have both safety guarantees and maybe the learning and fast computation time? Is that something we should strive towards?
Exactly. I think that's where, in general, most research groups are going, trying to combine it. Motion planning by itself can have at least collision guarantees, which is good, but you only get really safety and stability guarantees in combination with the control.
And do you know about, so what would you say is actually right now the best learning model in the world for drone flying? Or the best approach from your perspective?
I think it depends a little bit on the application you want to solve. For example, in our group, we use learning to really try to predict these interaction forces I talked earlier about. And then we try to figure out how can we use these things during planning and controls. I think that's a quite interesting way of thinking about it. I also believe that other methods like reinforcement end-to-end methods, like they are done for these racing drones, are very interesting because they really show us what is physically possible. And then we have a new upper bound that we can apply, maybe even to improve our traditional methods and have more guarantees.
So for people who don't actually know about racing drones, could you maybe elaborate a little bit on what they are and what they can do at the moment?
Right. So it's basically a sport where you put on first-person goggles, you see what a camera on board a drone records, and then there are racing tracks that are typically a sequence of gates, and you have to fly through them in a certain sequence. And human pilots just in teams try to race and try to get the best time. And just a few years ago, there has been the first drone that would be able to beat a human pilot in this sort of setting.
And as of today, basically, we have already solutions for those kind of drone racing scenarios.
With some limitations. So it's basically trained using reinforcement learning, knowing the racetrack up front. And then if you change a gate slightly, you would need to retrain from scratch.
So it basically assumes that you have always a static environment, and then you train on the static environment, and then you can perform, almost optimally in terms of motion on the static environment. But the moment you change a little bit something, then you have to do everything again from scratch. And how long would it actually take to retrain from scratch? Do you have some kind of ballpark figure there?
That depends on your hardware, but I think it was quite reasonably sized GPU cluster in about 24 hours.
So it's not something which you can just do quickly.
Not in a few minutes, no.
Yeah. So something which I really wanted to talk about is applications of large swarms of drones. So, I mean, your thesis was on the subject of motion planning for large teams of drones. So I guess you must have also thought a little bit about what we could potentially do with large swarms of drones. What would be applications in the real world? What could be even some products which we could make out of it?
So surprisingly, we have already seen some successful products in the entertainment segment. So we have these sort of drone shows. They exist both for outdoor kind of fireworks replacement and also for indoor shows. And then we have seen, let's say, promises of applications that haven't come through. Maybe the most prominent one is Amazon Prime Air. The idea was to kind of deliver the packages to maybe even a window and be much faster.
Yeah, what happened to that? So I still don't have a drone which delivers packages to my door. So
that is true. I from what I know, Amazon has made very good progress on the technical side, but there are many legal challenges if you want to operate in an urban environment.
Oh, really? So you would actually say that it's not a technical challenge, but it's now mostly like a legal challenge, a policy.
I believe so. Some is maybe intertwined with technical challenges. So we talked about these noise levels that drones have. That would be a problem. If we suddenly outside the window have 100 drones flying and they are as loud as they currently are, that's something nobody wants.
But I could also imagine that this last mile problem or the last meter problem basically would be very challenging for drones. So, I mean, flying somewhere roughly in the vicinity of like a house or something, I could really imagine that this could be possible. But then you have to like find maybe the front door of the house and really fly maybe underneath like some kind of I don't know, ceiling or so. So I think that might be also a super technical challenge. And do you think this is maybe something which is already possible? Or do you think that this is also still holding back drone delivery?
I think that's in principle maybe possible, but really make it to the point where the product is really hard. Most companies are considering more parachute-like drop-offs. For example, there's one company called Zipline based in San Francisco that uses fixed-wing drones, mostly in Africa, for medical supplies. And they are already operational. And they can cross very large distances to bring critical medication and blood samples to different areas.
So how does that actually work? So you said it's a fixed-wing aircraft. So basically it started somewhere and then just shot to like a
so it's basically
destination.
It gets started with like a little acceleration ramp, basically. And then it drops whatever it needs using a parachute.
And how does it actually get back to its starting position?
I'm not entirely sure, but it's mostly kind of in free space. So I assume it does rely heavily on GPS and just goes back to the starting point.
Oh, so basically it flies there, it drops it off via a parachute, and then it basically turns around, flies back. So it's basically like a usual aircraft.
Exactly, this is the only exception that is fully autonomous. There's no pilot on board, and the vehicles are fairly small.
And something which I also recently saw is that some research labs have developed like more natural looking versions of drones. Also some versions where you have like almost like a bird-like structure where the drones are not flying with like propellers, but really like trying to flap their wings and try to fly in that way. So what do you think about that approach? Do you think that there is like some benefits there to do it that way?
I find it absolutely fascinating. I also find birds in general very fascinating. And I think birds have capabilities that the current drones don't really have. One thing is that they can basically be completely silent if they want to. So the noise is the problem. Some of them are much more energy efficient. So there's some birds that can basically be in the air for hours just by using the updrafts very smartly. And so in that sense, I think it does make a lot of sense to use this inspiration. There must be a reason why after millions of years of evolution, we didn't end up with robots.
Sure, but we ended up with a lot of cars driving around, which evolution also hasn't come up with. Do you think that there are some applications maybe for drones which look like birds, which are not possible with normal drones? I mean, you already talked about energy efficiency, which is super important, of course, and also being silent. But do you think there's also like something else?
I think if you need to influence animals, it could be beneficial. For example, near airports, there's sometimes these problems that flocks of birds come and then airplanes can't really take off anymore for safety reasons. And then if you could have, let's say, even a remote controlled bird-like looking thing that makes sure that the flock moves maybe 1 kilometer away, then you wouldn't have these waiting periods.
And so here at the TU Berlin, you have built like a big drone lab where you try out all different things to see if your drones actually work, not only in simulation, but also in the real world. So tell me, how difficult is it actually to build such a drone lab? What are the challenges? What kind of equipment do you need for doing that?
So I think luckily it's not that challenging anymore because there's many labs in the world who have built it. So there's a lot of kind of knowledge in the community. What you typically need is some sort of safety structure. So usually these are nets. Often we use the same nets that are used for sports, like soccer games. You need some sort of tracking system that gives you the ground truth data if you fly indoor. So we use a kind of a motion capture system for that purpose. And I think, like at least here in Germany, one of the most challenging parts was to ensure the fire safety, because we operate with batteries that have a high energy density. So we have to be careful that if one of the batteries goes bad, that not the whole building burns down. And we have very strict regulations. So for all of the components you buy, you need to ensure that it follows the current guidelines.
I didn't know about that. And so what are you actually using for the tracking system? So what kind of system do you have in place, and how does it work?
So we use a motion capture system by a vendor called OptiTrack. It is basically a system of synchronized cameras that can detect, that operates with the infrared spectrum, and it can detect reflective markers that you put on the drones or objects of interest. And the output is very similar to a GPS, but with much higher spatial and temporal resolution. So you can track your objects up to 240 hertz with sub-millimeter accuracy.
Wow, that's not bad. And so what kind of applications or what kind of demonstrations can you already do in your lab, and what would you like to have in the future?
Right, so we mostly use it to demonstrate novel control algorithms, or that the motion plans we compute are actually executable on the real hardware. And so we have demonstrations where we have like object transport, where maybe multiple drones carry a payload, or demonstrations where we have very dense cases where drones are on a small volume and need to like move like in a puzzle-like environment to get out. What is entirely missing for us is really agility in both of these cases. So actually flying really, really fast, entering the task at the same time is something we hope to have in the future.
Do you think that there are still some things missing in the drone lab which are there in the real world, which are challenging for drones, and which maybe invalidate your controllers or your algorithms?
Yeah, absolutely. I mean, ideally, you wouldn't want to have a drone lab in the first place.
No.
It would be nice if you could go to any place indoors and outdoors and do your experiments. So we mostly have it for safety reasons because things don't work, and to kind of focus our research to areas of interest. For example, if we work on control algorithms, we do not want to limit ourselves to now also have to deal with state estimations, use the motion capture system. If you go with your drone outside, you have a lot of problems. There's like wind, there's like all the different visual experiences that you might have. There might be other entities that you don't control. If you fly low, like pedestrians, if you fly high, then maybe helicopters and these sort of things.
So talking about the real world, so I think one big application of drones at the moment is really in warfare. So we saw them, for example, in the one in Ukraine. So how do you actually feel about drones being used for war?
Like with every technology that is used for military purposes, it does make me sad.
Do you still think that there are maybe like some good applications of drones in war, for example? You could also use a drone for detecting mines.
I think that there can be benefits. Like traditionally, drones have been more used for passive things, not active things, like surveillance. And that can, in principle, at least reduce casualties, which is a benefit. And then the option you mentioned that, maybe just avoiding things instead of.
Yeah, but of course, so there's always like a human behind it, and depending on their intentions, it can always be good or bad, right? And I think search and rescue operations are obviously like super important and could be like done by drones, right?
Exactly, yes.
Yeah. I think I have never really saw like a real search and rescue operation with a drone. Are there actually some drones which could do search and rescue of a human being?
So it depends really on the catastrophe you are looking at. So I think for flooding, it's actually quite common just to, like similar to flying over with a helicopter, fly over with an FPV drone to just identify areas where people might be stranded and pick them up. After an earthquake, it's much harder, right? Because typically from above, you don't really see that much. And you would need to have drones or any sort of robots that can kind of move in, maybe also listen to see if you hear anything. And there I also haven't seen that many drones.
So do you think there's actually a business opportunity there to have like not like smaller drones, but like really bigger drones, almost like helicopter-sized drones, which could actually make some search and rescue operations?
Yes, but then you have to question why not use a helicopter? And a helicopter, in a sense, is also just like one form of drone or flying radar, right?
Yeah, but I mean, that could be very insecure. There are so many factors which could happen, like all kinds of disturbances. And I think a controller could maybe react better than a human being in those situations. So maybe it would be even like a safer option.
I think like one big advantage of the multi-rotors in particular is that they are, from the mechanical point of view, much simpler than a helicopter. So they can be more robust in these scenarios. I agree. When I talk about, or when I think about search and rescue and drones, I actually really more think about using them for exploration and not so much for picking up heavy loads like victims. So the idea would be really, if you have a building that collapsed, could you have a very tiny drone that then kind of goes through the cracks and like identifies areas of interest?
Yeah, but what about if someone gets lost on a mountain or so, or even like someone who's like lost at sea? So I think one big challenge there is, of course, that it takes like so many people to search all the area. And I think if we would have like a team or swarm of drones which could like see everything at once, it would be much easier to have like algorithms which detect something out of the ordinary.
Exactly. But even in that case, it would not be a drone that then really picks up the person, but that's more for quick identification and exploration.
And what would you say are the best applications of drones at the moment in civilian applications?
There is, of course, the entertainment business model, which I think does have a lot of advantages over fireworks in terms of at least safety and also just general pollution in little areas.
So you're talking about those big swarms of drones which can draw like a dragon or something in the sky, right?
Exactly. So, and that's like basically one of the like successful business areas for drones already. I would also say that in agricultural applications, it's quite interesting where drones are being used to also mostly monitor the health of plants. Depending on how time critical it is, you might or might not need many drones, right? You could have, of course, have one flying, but then you can't capture all the fields, for example. And I do think that there are other upcoming interesting areas for drone swarms. Like, for example, in manufacturing, it could be quite beneficial to have drones to either carry items around to make just-in-time manufacturing of smaller companies much easier, or to use it for inventory or other sort of surveillance operations compared to like traditional like wired camera systems. It's just much more flexible what you could do.
I always heard that one of the big problems, of course, also if you have a small drone, you can only have like a small battery inside of it. What are actually the times of how long a drone can fly at the moment?
So it really depends on the size and also the type of the drone.
Yeah.
So what we use in the research lab can fly about 5 minutes. Slightly larger drones that you commercially buy to like film yourself or other people can fly maybe 30 minutes. But you can also see that like more traditionally powered drones like airplanes can fly for several hours, right? And of course, there's a higher energy density of the fuel they use in combination with the technology of it being fixed wing. And then I would also consider blimps as a form of drone. And these,
so what is a blimp actually?
Like you have like a hot air balloon, for example. And they can essentially fly almost forever, right? They're very energy efficient.
So you would say those are good things if you consider like long lifetime applications.
For kind of surveillance, they're quite nice. Like, for example, weather balloons, they often use these sort of technologies just to gather data over long periods of time.
And let's switch a little bit to a different subject. So something which I always like thought about is how you can maybe like have some synergies between different research fields. For example, with drones, I could imagine that there might be some synergies with material science. So for example, if you have like drones which are very hydrophobic, so all the water is just like repelling there. So maybe you could also make them like dive around. So did you already like think about something like that?
Not personally, but I've seen many interesting areas. There are really flying vehicles that can also operate as a submarine. I think there's a lot of synergies that just also comes from kind of mechanical and electrical engineering. Having better batteries has directly an impact, not only about energy density, but also just about currents that you can draw, because for drones, you really need
for sure
very fast acting motors, so you need high currents that you can draw consistently. And also we often see in that general area large improvements just by better propeller design or other kind of mechanical tweaks that nobody has thought about before.
So what is some kind of research which you're still pursuing at the moment, which we haven't yet talked about? Are there like maybe some projects which you are currently working on?
I think we talked about the main projects which is basically trying to get many drones in a small volume, operate safely. We also have projects that go more in the direction of security. So the question is, if you have kind of a drone you buy off the shelf that follows you, how sensitive is that to adversarial attacks? And so we have some research that shows, yes, it's very sensitive and it's basically dangerous. And that, of course, us as researchers now also should, tell us here we need to do some improvements on the algorithms to make it safe by design.
Yeah, that makes sense. So that the drone is basically not hackable from the outside. Yeah, and something else I wanted to talk about. What would you say is maybe like the most impactful paper you have ever written or which your lab has ever produced?
That's interesting because impact you really can only measure like a long time later. I think like the highest cited paper was a paper called Crazy Swarm, which was not very scientific, but proposed just a software infrastructure to fly many drones. And many people use it to do their research in different areas. And so I would say it's probably the highest impact.
And so what was actually the content of this paper?
Scientifically speaking, not too much. It just describes a system architecture on how you can fly, in this case, up to 49 drones that are all commercially off the shelf available. And also release the software. So whoever uses the software is citing the paper.
And what would you say are some things which you still want to accomplish in your career, like long term? Maybe writing a book or extending your drone lab?
It would be very exciting for me to see some of the algorithms that I develop in the real world. Like it's my time at NVIDIA that basically happened that my master thesis became part of a product. So it would be nice to see that in the area of robotics now as well.
And so if there's maybe like a student who's really interested in drones, what would you maybe give as an advice of how you could go into drone research? What kind of topics should they study? What kind of subjects should they get familiar with?
I think like they first have to really understand the physics of drones and how to do all the basics, like how to write a simulator, how to write a controller, state estimator, and so on. And in fact, we are just in the first semester now where I have a class that the students learn these topics.
And yeah, I would say one big indicator of research success is really this H index. So how do you feel about the H index, especially when we talk about quality versus quantity of papers? Do you think this is really like a good way to track productivity, or are you more a bit critical about it?
I think like all metrics, it has its pros and cons. I do use it to get like an idea of another researcher on kind of what they're up to and what are even like also variables that are influential, which indirectly the H index tells you. I don't think it should be really used to compare people, because even within robotics, depending on which subfield you are in, you can end up being brilliant but have an entirely different H index than somebody else.
And so what would you say, how would a typical day for you look like in your research lab?
So we try to structure it inspired by industrial positions. We always start at 9 a.m. with short sync up. I call it not stand-up because we're usually sitting. It's at most 10 minutes long, and everyone in the group just said what they did and what they're planning to do, and if there's any need to discuss. And then we use kind of normal tracking software to figure out what we should be working on. And so I typically have like time blocks where I say, okay, now I do more administrative tasks. or now I work on teaching, and now I do research areas. And then I try to, within the time block, try to work on to-do items that reflect this area.
And do you actually also have maybe a meeting once a week where someone is like presenting their research?
Right now, we jointly have a meeting with another robotics group once per week, where we also give these more scientific updates. We also have a weekly paper reading group where we all have to read the paper, and then we use about 1 hour of our time to just kind of discuss what we have found.
And in terms of success, what would you actually say is your definition of success? And when you have defined it, how would you say that you actually measure up to it?
So for me, it's very abstract. Like I would say I'm successful if other people value my work. And so in teaching, that can be a student that says, comes after the course is over and says, so I really enjoyed it, I learned a lot. In research, it can be either people citing your work, or you're going to a conference and somebody telling you, oh, I was like inspired by this or that. And then, let's say, traditional engineering software development, it's like basically your GitHub stars or forks or whatever. And yeah, I hate to really like put a target value on it, but I do get this positive reinforcement feedback occasionally. And I feel that I achieved what I wanted to achieve.
So you would say your target in life is basically being useful for the robotics community, or just being useful in general?
Of course, in general, but then you have to limit yourself to the areas where you're actually active in, which is kind of locally the education at TU Berlin, and then more broadly, of course, the research in robotics.
I think in the beginning you already talked a little bit about that you had some mentors. What did you actually learn from those mentors, and how did they actually help you in your career?
I think like you never really know what you learned exactly from whom. And there's a lot of influence that I feel I got from many different people in different areas. Sometimes it's even just based on a very short interaction. I think I like a lot of technical skills and also social skills I just kind of picked up by observing how other people behave. And then if I like it, I think back and I just copy it.
So for you, mentoring is basically imitation learning and just trying to like get their ways, so to speak.
In some sense, where I define the reward locally.
And was there maybe like one person who really deeply inspired you?
No, it's really just a mix of people for different.
A good mix of mentors, basically. Is there maybe also something which you do to like counterbalance this whole work as a professor?
Yes, so I have a young child at home. We do enjoy tinkering with Legos quite a bit. I started woodworking a while ago.
Nice.
I do like hiking.
So what did you build in woodworking?
Mostly furniture at home.
Nice. So you don't have to buy it anymore from IKEA. You just do everything by yourself now.
It's more expensive. The material is more expensive than the final product.
I also found that out. So what kind of hikes do you usually do?
It depends on where I am. So in the United States, there were a lot of like national parks I visited. I did longer hikes. Here in Berlin, I go more on the shorter ones, so Counterbalance.
And was there maybe like some super memorable hike which you have, or what was the most memorable hike you ever made?
I once did like a 5-day backcountry hike in the Kings Canyon National Park.
Where's that?
That's in California.
Okay, nice.
Near Sequoia National Park. And we did have an encounter with bear mama and cub. all friendly from both sides.
Yeah.
And
Okay.
that was
That sounds
amazing experience.
Yeah. So what kind of bear was it? Do you remember?
Well, I didn't get so close to really find out.
Yeah.
But I believe it was a brown bear.
Okay. Nice. So you survived that.
Yes.
You mentioned already mentors, but is there maybe some kind of life lessons or so which you learned in your life, which in retrospection you think, oh, that is something which I should have learned much earlier?
I think it's important not to really question what you have done, because you can't really go back and change it and see what's a different outcome would have been. And also it's important to remember that most of the things we do in research, at least, is more similar to a marathon and not a sprint. So
For sure.
you just have to plan a bit and then execute it and just avoid the urge of giving up.
I think that was everything from my side.
Thank you for having me, and I'm excited to listen to all your other podcasts.